Well, hello everybody. I think it's time that I follow up my original discussion prompt about the nature of the derivative and the slope of a curve. So my discussion prompt was that suppose I've got this curve, f of x is x squared plus 3x. And I wrote this down and I said, can I use this to calculate the slope of the curve at this point where x is 3? The point is x is 3, y happens to be 18, but that point. And I wrote down this formula. I said, is anything missing? Left as an open question. Is it totally correct? Again, left as an open question. And what's the slope of the curve ultimately at this point? Okay, so I did leave some things out of that. There are some things missing that need to be there. And let me show you over here what they are. Okay, so here is the revised formula. First, the derivative, the thing that tells us the slope of a curve, is expressed in terms of a limit. The limit must be there. Okay, so it has the stuff that I had, but it must involve a limit as h goes to 0. So you notice I had this h in here, x plus h squared plus. That has to go to 0 ultimately in order to find the derivative, which is what tells us the slope of the curve. Okay, another thing that I left out is that notice that here's our generic formula for the slope of the curve, or the derivative as it's otherwise known. It's the limit as h goes to 0, f of x plus h minus f of x over h, where f of x is the equation, the formula for the original curve. See how there's that subtraction right there? So this part right here is f of x plus h. And this part right here is f of x. But that subtraction must apply to every single term in f of x. When I wrote this original formula down, I didn't put the parentheses to indicate that that minus, that subtraction, applies to all of that. So those were the two things I left out. And they're in red here. The limit as h goes to 0, and the parentheses like so. So what you see here is the limit as h goes to 0, f of x plus h is this part, minus f of x is this part, parentheses indicating the minus applies to all those terms over h. So that'll do it. That's what I was missing. Now, from here, let's evaluate this down to its reduced form so that we can use it to find the slope of the curve. So to do that, I would have to square x plus h. I'd have to multiply it by itself with FOIL multiplication, and I'll get this. I'd have to distribute the 3 across there, and I'd get that. And again, this minus applies through all of that. Okay, so I get this. And then I notice that some of these terms cancel. There's the x squared and the negative x squared. There's the 3x and the negative 3x, and that's everything that cancels in that step. And I'm left with this. There's a little bit more canceling that can be done. The way we understand a fraction like this is that each of these individual terms gets divided by h. It's not just that any two of the h's cancels and you're done. This is 2xh over h, which is 2x. H squared over h, which is h. 3h over h, which is 3. Now, I've been carrying this limit along the whole time, knowing that it was only in the end that I would use it. So now that I've reduced this as much as possible, it's time to let h go to 0. So imagine then there's h. Imagine if it went all the way to 0, what would happen to it? It would disappear, and you'd be left with 2x plus 3. Okay, so there is your derivative. There's the thing that tells you the slope of the curve. Now to summarize it, f of x is the curve. F prime is the derivative. F prime, F apostrophe, that's the symbol we use for the derivative. That's the slope of the curve, okay? Now, my final question in my prompt was, what's the slope of the curve at the point where x is equal to 3? So I would just have to take my formula for the derivative and plug in 3 for the x. And if I do that, this is what I get. 2 times 3 plus 3, which is 9. So 9 is the slope of the curve at that point. Now, if you're going to do anything with math, it's important to understand the concept of slope. So when I say that the slope is 9, here's what I mean. The curve at this point is such that you run 1 and rise 9. That's fairly steep. I mean, slope no matter what is rise over run. So if the slope was 9, I would be saying a rise of 9 is associated with a run of 1. Now I got my ruler out and I actually drew that. It's like, so here's 1 unit of run and here's 9 units of rise. And that blue line right there is how steep the curve would look at that point. Let's see if that's true. Seeing is believing. So here I went in an online graphing calculator and I graphed that parabola, okay? And I was aiming to tell you the slope of the curve at the point where x is 3. So I'm going to zoom in on that point. Let's see. So 3 is about right here. So, all right. So here's that point. See, 18. So this point is 3 for x, 18 for y. And with the derivative, do you know what this h going to 0 actually means? It means that I'm not just looking at the curve, but I'm looking very close. I'm zooming in very, very, very close. You know, this whole thing right here, this equation x squared plus 3x, is a curve, but if you look close enough at any point, it will smooth out into a line, and that's what I'm seeing right here. But let's see if how accurate I got it. So my claim is that the curve looks like that, okay? And let's see. So here we go. I'm going to see if I can overlay this. And not bad. So here's what I want you to imagine. So I zoomed in really close to that curve at the point where x is 3. And I'm saying it looks like this line in blue right here. But imagine, so there's the curve on the grapher right there. Okay. And then imagine, like, if you continue on what I drew to scale with my ruler, keeps going, and say I keep going, and then it picks back up, right? So I mean, I used a ruler to draw this. It's pretty good, I would say, for having done it with my drawing pad and a ruler. But that's what I was saying would happen, that with the derivative telling me the slope is 9, if I took that curve, and if I looked at it very close at that point where x is 3, which I have here, then this is basically what I would see, and that in fact is what I am seeing. So, like I said, I hope that you see it the same way I do, which is that seeing is believing.